So my name is Jim Adams, and I've been invited to talk to you today about space. I've received a number of questions, but Harry also told me that there was interest in the recent discovery of an exoplanet by the James Webb Space Telescope. So what I thought I'd do is start today and tell you a little bit about myself, and and then we'll talk about what an exoplanet is and how you discover them. And then I have a list. Anyway, let's get started. I have put together a small presentation, and I've left that with Harry, and you can use it however
Okay.
you like in the future.
Okay,
Yeah.
thank you so much.
Moan. Okay. Oh, somebody has an open mic. There we go. All right. So I retired from NASA in 2016, and as my last job with the agency, I was the Deputy Chief Technology Officer for NASA, which means that anybody who was working on new technology for the agency was working for me. Before that, I was the Deputy Director of Planetary Science, and that's what I actually view as like the best job I had while at NASA. And that meant that any spacecraft, unmanned, that left the Earth and went to another destination, like Mars or Pluto, or Jupiter, they all reported to me. So,
Okay, Jim, you can use because the other participants unable to mute their microphones. That's why I muted all. You can do your presentation, please.
all right, testing 1, 2. Can you hear me now?
Yes, yes.
Awesome, good. Okay. Well, anyway, we can talk briefly about who I am and what I did for NASA, and then we'll talk about the question with regard to exoplanets. One of the cool things about my job was I got to play with rockets. Some of the stuff that I built flew on the space shuttle. Some of the stuff that I built flew on this rocket here as an Atlas V. And that's what it looks like when you're watching your spacecraft, which sits at the very top of that rocket, take off. And that happened to be a launch of a spacecraft that we were sending to Jupiter. That's what it looks like inside of a control room. It's me working with the head of the agency, Dr. General Charles Bolden, and we were getting ready to launch a rocket on that day. And how many of you would like to see a rocket launch?
So, how many of you just raise the hands?
Just raise your hand if you'd like to see a rocket launch. Nope. Okay. Anyway, this is what it looks like to watch a rocket launch. Oh. Try this again.
10, 9.
Can you hear that?
7,
Yes.
6, 5, 4, 3, 2, 1, 0, and liftoff of the Delta II with Grail. The journey to the center of the moon.
Chamber pressure rising in all 6 grounded solid motors. Good chamber pressure on the main engine. Good chamber pressure on both verniers. Good chamber pressure on all 6 grounded motors. 20 seconds into the flight. Yep, 29 seconds. Mark, 29 seconds. Mach 1. Vehicle now going transonic.
So I'll stop it there and I'll just say, the reason we put stuff on top of rockets is because you have to get away from the Earth's gravity. And these things are so powerful that in just 29 seconds, it was going faster than the speed of sound. So, oops. There's also, there's another kind of rocket that we launched. This one also went to the moon. When you watch it, when you see a rocket launch, everybody has to be away from it by about 5 miles in case it blows up. But sadly, this frog did not get the word that he was supposed to be away from it. So he got kind of blown away when we launched this one to the moon. Got to do other things like sit in control rooms as we flew by comets. And I worked on the Hubble Space Telescope. So now we're going to talk about our question of the day is about exoplanets. And an exoplanet is a planet like our solar system has that is around another star. And it wasn't until the 1980s that we actually knew there were other planets around stars that we were able to detect. And one of the ways we detect them is by using telescopes, and other ways is we use our spacecraft with telescopes, and other ways that we detect them is by using ground-based telescopes. This is a picture of the Hubble Space Telescope, which was the most powerful telescope in the world until we launched the James Webb Space Telescope. I see somebody has their hand up. I think, Harry, are we taking questions at the end? Is that right?
You can take the questions after the presentation.
Okay, all right. So that's the Hubble Space Telescope. It has a mirror that is the same size as one of these segments on the James Webb Space Telescope. So the James Webb Space Telescope is far more powerful than the Hubble Space Telescope. And we'll get into that in a minute when we get into your questions and answers. This gives you an idea of just a comparison of the mirror size. The Hubble Space Telescope has a mirror that's about 2.4 meters across, and the James Webb Space Telescope has a mirror that's about 6.5 meters across, made up of all of these little segments. And in comparison, in the background, you see one of the most powerful telescopes in the world that's on the ground, and it's 10 meters across. So it just gives you a sense of size. The reason that size matters is because the more light that you can gather, the better you can see objects that are further away. And so you can gather more light. You don't have to wait as long to get the picture, as well as you can see deeper into space. So remember, I don't know if I was muted or not, an exoplanet is a planet that orbits another star. And recently, once the James Webb Space Telescope got on orbit and it started taking pictures of deep space, it found two different kinds of exoplanets. And so when somebody said to me, gee, can you talk about the new planet that James Webb Space Telescope has found? There's actually been two. There's one that was announced in September, and there was one that was announced in January. And they're two different kinds of observations. There's two different ways of looking at things in space. Actually, there's lots of different ways, but the two that we're going to talk about today is direct imaging. That is, you take a picture of the thing that you're looking at. And so at the lower left-hand side of the screen, you see this artist's concept of what a planet around another star might look like. And if you could just take a picture of that little planet, then that would be direct imaging. The other way of finding or taking a picture of an exoplanet is to watch it cross in front of its star. And so the star that it's orbiting around will dim just a little bit as the planet moves in front of it and across it and then off the other side. When it does that, and you take a picture of the change of in the starlight, then you can actually see the starlight dip down a little bit. That's called a transiting occultation measurement. And so that transit means it's cutting across, and occultation means it's blocking some of the light. And that's the way that most planets are observed today, because the telescopes have to be very, very big in order to take direct imaging. So the exoplanet that was announced in January was a transiting exoplanet, which means that it was actually smaller than, was one of the smallest planets we've observed with the with either the Hubble or the James Webb Space Telescope. And what you can see in this picture is that over on the left, that's the data taken as the planet approaches in front of its star. And then when it gets in front of the starlight decreases, and that's the dip that you see there. And then as it leaves from in front of the starlight increases and goes back to where it was. And that's how we know that there's a planet there. It tells us a lot about how fast the planet is moving and maybe how big it is, and a number of other things. So that's the common way of taking pictures of planets. You basically infer that they are there based on the data that you get by watching their star dim. Another way is to take a picture directly of it. And it takes a very big telescope to be able to do that. James Webb Space Telescope is one. And that's what was announced in January, I believe. Yes, no, I'm sorry. That's what was announced in September of last year. And so these are pictures taken in different wavelengths by different instruments that are on board the James Webb Space Telescope of the same planet orbiting the star that's known as HIP 65426. And so they give the planet and the name of the star here, HIP 65426, and then they say B, because it's the second object that they found in that solar system. So, so that was historic, even though they look like fuzzy blobs. That was historic that we were able to see the planet that was orbiting this star. Now, in order for somebody, for the James Webb Space Telescope to see that by direct imaging, that planet, that exoplanet, has to be very, very big. Because right now, today's technology, we can't see planets that are the size of Earth with the James Webb Space Telescope. So I think I have, yeah, I have a comparison here. So the exoplanet that was announced in September of last year was viewed by direct imaging, and it's considered a gas giant. Well, a gas giant, we have two gas giants in our solar system. One is Jupiter and the other is Saturn. And it means you can't actually walk on the surface of them. They're basically big balls of gas. And that planet that we took an image of, I'll show you here, this planet here, this exoplanet that's in all four of these images, is 6 to 12 times the size of Jupiter. It's enormous. And 1 year, that is one time around its star, is the equivalent of 631 years here on Earth. So you have to have, you'd have, if you lived on that planet, which you can't, but if you lived on that planet, you would only age 631 years in a year. It would take you 631 years before you'd have a birthday. So it's estimated that that gas giant is 15 to 20 million years old. Well, that's interesting because our Earth is estimated to be 4.5 billion years old. So this is likely a very young planet. And if you wanted to go there, it's 385 light years away. And that's a really long way. That's 385 times the distance that light will travel in an Earth year. So it's a pretty long way. If you compare that to the other measurement that was made, remember we talked about a transit occultation. This planet, this exoplanet was announced in January. It was measured by transit occultation. It's considered to be a rocky exoplanet about the same size as Earth, which is very interesting. And if on that planet, if you wanted to spend a year there, you'd only be there for 2 days on Earth. That planet is moving very fast around its star. And at this time, we don't have the data to tell us how old we think that planet might be. But we do know that it's only 41 light years away. So that's the comparison between the two kinds of exoplanets that were announced. One is a gas giant that's much, much bigger than even Jupiter. And the other is a rocky planet that's very much the size of Earth, but it's moving really fast around its own star. And just for reference, suppose you wanted to go to that planet that's only 41 light years away. Well, the fastest thing ever to leave the Earth was the New Horizons spacecraft that we launched in 2006. And it took that spacecraft 9 years to get to Pluto. So if you did the math and you figured out how far 41 light years is in distances compared to Pluto, you could figure out how long it would take you to get from Earth to that exoplanet. And if you do, and I did the math this afternoon for you, and it would only take 398 years for you to get from Earth to the exoplanet LHS 475b if you traveled as fast as the New Horizons spacecraft did to get to Pluto. So that's the comparison, and that's the discussion about exoplanets. The question is, why are we interested in this? And this will be the last slide, and then we'll start getting into questions. The reason that we're doing this is we're looking for planets around other stars that are like ours, that might be habitable, not because we want to go there, but because we think maybe, since there's life here on Earth, maybe there might be life in other solar systems. And that's the main reason why we're taking pictures of stars and looking for planets around those stars. I think, Harry, I'm going to end there. And I think we can get into the questions and answers. So some great questions.
Thank you. Thank you so much for your presentation. So Jim, welcome back. Okay, Sivarageswara garu, go ahead. Sir. Okay, Sivaraj, go ahead.
ఓకే సార్ సార్ హరికృష్ణ గారు ఓకేనా
Please, sir, you can go ahead and ask the question.
ఓకే ఓకే
Okay, Sivaraj garu. Okay, you come. So yes, it looks like they are not responding. I would like to ask one of my students is going to ask the question. Say good evening, sir.
Hi, sir. Good,
Good evening.
good evening, sir.
Ask. Okay, just a minute. Okay, Jim, you can respond. Yes.
All right. Can you hear me now?
Yes. Ask.
I have a question, sir. Can I
Ask.
ask you?
Ask.
Sir, please explain the interpreted in the Interstellar movie.
Ask.
So, can you repeat your question because I did not understand?
Sir, please explain Tesseract interpreted in the
Oh.
Interstellar movie.
So the tesseracts, is that right? So if I've understood the question correctly, a tesseract in mathematics is a way of representing a cube in 4 dimensions or 5 dimensions, I think, in 5 dimensions. And it's a way of trying to visualize the way things might look in dimensions, dimensional space that we don't have right now. So that's what it is in mathematics. In science fiction, in the movie Interstellar and in some other movies, they use the idea of a tesseract to imply that there are special ways that people in other dimensions or life forms in other dimensions can communicate with human beings. I have to say that's right now, that is science fiction. But that doesn't mean that it isn't possible someday to communicate across dimensions. It's just that we don't have the physics yet today to be able to do it in real life. It's fun though to think about when they work that sort of thing into movies. So that's a really good question too. I hope you like science fiction. I sure do. And if you look at some of the technology we have today was actually predicted first by science fiction. So maybe someday a tesseract will be a real thing.
Thank you.
Thank you.
Thank you very much.
Okay, Sivaraj garu, are you still available? Sivaraj garu. Okay, you can respond. Sivaraj garu. Yes, you can ask a question.
ఓకే
Oh, you're on mute.
Yes, yes.
Good evening, sir. I have a question. Can I, sir? For
I can-
interplanetary travel or interstellar distance is the main barrier. Is it possible to conquer humongous hurdle to mankind? Is drive technology possible, sir?
Yeah, It's an interesting question as well. So many really good questions today, Harry. I'm telling you, these students are thinkers. And if you remember the last slide, or one of the last slides I showed you in my PowerPoint presentation, I said it would take 500,000 years for us to get to the exoplanet that we were talking about. If we traveled as fast as we possibly could, as we know how today. And you're exactly right that it is the extreme distance that limits us from being able to go to these places that we can see with telescopes, which is, just as an aside, it's amazing that we can see those things. And if you think about what happens is there's a planet 42 light years away. The star it's orbiting shines on that planet, and the planet reflects light that then travels for millions of years to end up in a telescope that enables you to be able to see it. And in that way, it's a little bit of like a time machine, isn't it? So actually 42 light years, it's only, the light that you're seeing is only 40 years old, but you're seeing that planet as if it was 40 years ago. And so what would be interesting is if you could travel all the way up to the speed of light, it would still take you 40, 42 years to get to that exoplanet that we talked about today. So in Star Trek, which is again science fiction, they talk about warp speed. And if they say warp 1, what they mean is you're traveling at one time, you're traveling at the same speed as light. If they say warp 2, then they mean 100 or 10 times the speed of light, and warp 3 is 100 times. And it just keeps on going by factors of 10 that way. Is that possible? Not today, it's not. Not until we come up with some new sort of physics. There are scientists that are testing some theories that would enable us to move particles, very, very small things, up close to the speed of light. That would cut the time it takes to get to places like Jupiter and Pluto down to months instead of years. But that still would not conquer the distance even just between us and our closest star. So it's a thing where we are going to have to continue to invent technology that would help us go faster and faster. One of the important things to remember is if you can get up to speed and go really, really fast, you can cover that distance in a shorter amount of time. But you got to remember, you have to slow down when you get there. And so that becomes just as big a problem as getting up to speed. So great question. Harry,
Yeah,
what do we got next?
Yeah, Kadavaram. Yes, you can. Yes, you can.
Good morning, sir.
Good morning.
Good evening.
Sir, it's my pleasure to speak to you, sir.
It's a pleasure here too.
Sir, can I ask you a question? Is time travel possible?
Oh, until we break the barrier that we seem to have with the speed of light, then I would say no, time travel is not possible. Again, there are scientists that are working on trying to travel faster than the speed of light. And when you do that, then classical physics says that you will be breaking the time barrier. But all of these things are fascinating because they are things that were conceived in the imagination of man. And so we have human beings that have an imagination about maybe being able to travel faster than the speed of light. Well, just because I say today it's not possible doesn't mean that in some time in the future that we won't be able to. And I think that what we all need to be doing is raising generation upon generation of physicists and space scientists that will be looking at whether or not we can break those barriers that keep us basically tied to this solar system right now. But it would be cool if we went from the International Space Station to the moon, then to Mars, and then to another star. And hopefully we'll be able to
Thank
figure
you.
that out.
Thank you.
Thank you. Thank you, sir.
Dugirala girls. So raise your hand. Yes. Yes, you can. You can ask your question.
Good morning, sir.
Good morning.
I have a question, sir.
Go ahead.
How could solar Parker probe withstood against the enormous temperature of corona?
Yeah. You know, I actually worked on Solar Parker probe for a little while. And the probe has a really unique covering, like a shield in front of it, that enables it to withstand that heat. But you know, withstanding heat is a combination of not only insulating from that heat, but also reducing the amount of time that it's exposed to the heat. So what the Solar Parker probe does, which for the others that don't know, it dips down and goes into the sun's corona. And so it's actually touching the sun. It's moving so very fast. So we make it go really fast when it does that. So it goes down and in and out. And so then once it comes back out, the surface starts to cool off again, and they get it ready to go down and dip again. So that's how the Solar Parker probe, it's a combination of the materials and the time of the exposure to the heat.
Thank you. Prakash Rao. Prakash Rao. Yes, please.
Okay. Sir, shall I ask you a question?
You may.
Recently, NASA confirms.
Oh boy, hang on,
There is an echo coming from your side. Could you please ask clearly, please? Ask.
Recently, NASA.
English.
Boy, I can't,
Yes,
I think he's muted.
Yes, there is something wrong, I think. Yes, Pusuluru. Yes, Nirakshan Rao garu, go ahead and ask the question. Yes, you can ask. I am trying to unmute your microphone. Yes, you can ask.
There we go.
Harikrishna, we are ready to ask the question.
Yeah, please ask.
Good evening, sir.
Good evening.
I have to ask you a question.
Yeah, please go
I
ahead.
have to ask you a question.
Yeah, go ahead, ask me.
Go right ahead.
What is the result of Large Hadron Collider experiment?
I saw that question in advance. As somebody who's well informed, I have to tell you, I don't know. The Large Hadron Collider is a project of the CERN in Switzerland, and it's fundamental physics investigations, and really less to do with space and more to do with trying to understand the makeup of atoms and subatomic particles. But I will tell you that I have a friend that works on the Large Hadron Collider in CERN, and perhaps if Hari's interested, we could have her come and talk to you about the LHC someday. So
It's our pleasure. It's
Yeah.
our pleasure. Yeah.
So thank you very much, sir.
You're quite welcome.
Yes, and if you are still interested, actually, I have, you please raise your hands, those who are ready to ask the question so that I can unmute. Digral Amyogar.
James, uh, sir, I think voyages, both voyages and pillars of creation, Eagle Nebula, are having a sentimental attachment to astrolabers.
So-
Where is Voyager now? How far it is traveled? Is it still in active mode? And another one is Eagle Nebula still there in the universe?
Okay, so you're breaking up and I'm not exactly sure what the question was that you're asking.
Srinivasa Garu, please ask one more time.
Yeah. One more time.
Okay, one more
Voyager,
time.
sir, Voyager spacecrafts are the sentimental, we have sentimental attachment to astrolabers. In fact, is it still in active mode? Is it sending pictures or any data to NASA?
Oh, are you talking about WISE? The WISE
Voyager,
spacecraft?
Voyager. Yeah.
Yeah. Let's see. The WISE spacecraft was originally an infrared telescope that we kept it cool by having a block of solid hydrogen that kept
Yeah.
the detector cool. Eventually, that warmed up and the hydrogen bled off, and we repurposed the WISE telescope to look for asteroids. And the end of that mission has come now, and the WISE telescope is not operating any longer, to my knowledge. All of these things that we design, they have prescribed lifetimes, and the WISE outperformed its lifetime and did really well and contributed a great deal to our understanding of asteroids and infrared astronomy.
Okay, thank you. So, Pedavaram.
Password 1974.
Good evening, sir.
Good evening.
I would ask you a question, sir.
Go right ahead.
Sir, what is going on in ISS and what is the lifetime of ISS?
Oh, yeah. Also another good question. You know, when I got out of college, I worked for a company called General Electric, and GE was building spacecraft. And one of my very first jobs was to help design the International Space Station. That was back in 1979, right? Well, we first started assembling the International Space Station in 1998. So it took from 1979 to 1998, what is that, 19 years, before we actually started building it. And the first mission went up to start building the ISS in 1998. And if you look at when the International Space Station partners have agreed that the end of the ISS should come, they've said that should be 2031, right? So you do the math, and that comes out to about 33 years is the lifetime of the International Space Station. Along the way, there are things that we have to repair. Solar arrays don't work, reaction wheels, these big things that keep the station stabilized, they have to be replaced. Electronics wear out, those sorts of things. So we have a program to do the maintenance necessary to extend the lifetime of the ISS. And it's very probable, if you ask me, that we'll get really close. We'll get really close to 2031, and the partners will again agree to extend its lifetime out beyond 2031. Because fundamentally, as long as you do the maintenance, there's no reason it couldn't continue to operate, except that the countries might want to go do other things by then, hopefully around the moon. Yeah.
Thank you.
Thank you.
Z.P.H.S. E-money, Z.P.H.S. E-money, please respond. Raise your hand, Z.P.H.S. E-money. E-money. Okay,
Sir, I want to ask a question.
yeah, please go ahead.
Recently, NASA informs DAFT mission impact changed in a asteroid motion in a space. Can we use this technology to avoid future impacts, particularly during Apophis? Asteroids fly by in April 13, 2029?
Yeah. So first thing I'm going to say is that the more we observe Apophis, the more we are confident it's not going to hit the Earth. It's going to come very, very close, but it's not going to hit the Earth. So I don't think you need to lose any sleep over that. It's don't worry, we're safe from Apophis. But it is very important that we understand the physics of asteroids so that if we ever find one that's coming inbound towards the Earth, that we have a way of redirecting it. And one of the things is, if you find it early enough, you just have to give it a little bit of a nudge, because that nudge over time gets multiplied to bigger and bigger separation angles. And you just give something a little nudge and eventually it'll just move out of the way of the Earth and they won't collide. And that's what the DART mission was intended to prove that we could do. But we did it on the moon of an asteroid that we knew was not going to hit the Earth, so that we were safe. Just in case something went wrong, we wanted to make sure that that if we hit it, it wasn't going to come back in and enter into the Earth's atmosphere. So the DART mission was very successful, and that's exactly why we did the mission, was to prove that we could do it if ever we needed to, if we found an asteroid that was inbound that might harm human populations.
Thank you. Donna, I think somebody texted Donna. Please respond. Yes. Anybody is interested now? Raise your hand so that I can unmute. Yes. Somebody texted. Raise your hand so that I can call you. Yes. Yes, you can.
If Apophis
Ask please.
yes, humans and animals also extinction.
So I am sorry, there is an echo is coming from your side. So if you are interested, please text me in the chat box, and so that I can call you by your name. Meanwhile, Z.P.H.S. Ilavaram.
Hello, sir. Hello, sir. I am Lohita Girija. I am a 9th grader. Could you allow me to ask a question? Sir, please explain black holes, quasars, and blazars.
Okay, can you hear me now?
Yes, sir.
Yeah, could you please ask your question again?
Okay, sir. Sir, please explain black holes, quasars, and blazars.
Please explain.
Black holes, quasars,
Oh, black holes.
and blazars.
Yeah. Right. So, so black holes are thought to be the formation of a dying star, where it collapses in upon itself, and the more it gets closer and closer together, the more gravity it attracts, the more things it attracts, the more falls in, the bigger it gets, and it continues to compress itself, and it becomes so massive that it affects space and some think even time in the vicinity of the black hole. In fact, part of the reason that you see our galaxy has a spin to it, if you look at pictures of our galaxy, it has these spiral arms. Part of the reason for that is that there is a supermassive black hole at the center of our galaxy that keeps everything in our galaxy kind of like in order. And so, we couldn't exist in the Milky Way the way we do if it weren't for black holes. And there was something else that you wanted me to talk about. Quasars and blazars. I have to tell you, I'm not a radio scientist, so I really don't know that much about quasars, other than I know that they're regular radio emissions from possibly black holes deep into space. And as they spin, this radio emission comes and goes, and it's you can actually time them so you have an idea of when they're going to come back, simply because they're so repeatable. Yeah.
Thank you.
It's a good question. Yeah.
So any more questions? Please raise your hands if you are interested. Just raise your hand so that we can call you. Yes.
So, and Harry, we're starting to run out of time.
Yeah.
But I have a question for everybody. So I want the last question. I want to ask the last question.
Please go ahead.
Oh, well, I thought we might squeeze one more in. Is there somebody else that wants to ask another question?
Yes. MBO garu? Yes, sir.
We have two questions, sir. Sir, have you watched Green Comet?
All right.
It
So
is
I did
today a green comet, C2022 Z.P.H.S comet. Now it is nearer to our Earth orbit.
So I haven't yet. Have you had a chance to see it? I live outside of Washington, D.C., and there's a lot of light pollution. And so I'm not able to see it. But I'm hoping that places like where you're at might be able to see it and get some good pictures.
Today it is located in Taurus constellation, but we are unable to capture it, sir. That's the question, sir. Sir, now our students are euphoric conditions, sir. With you, interact with you. We are awaiting for our next encounter to you, sir. Thank you very much for sparing your priceless time to our students, particularly.
Thank you very much. It's been a pleasure talking with you all. I see somebody's made up a sign with my name on it.
Yes,
thank you.
It's my students. In fact, they made it with the colorful papers.
Thank you very much. So, so here's my question to you all. Raise your hand if you're going to study science, math, engineering, and technology at university. Raise your hand. I want to see future scientists coming from India. So, yeah, I see several. All right. I think that's an important career path. And it's not just good for you, but it's good for humanity. So in my book, if somebody came to me and said, what should I study? I would say physics or chemistry or mechanical engineering or anything that will ultimately help us understand space and our place in the universe. And I hope that someday that will be you. So everybody, have a wonderful day. Hari, thank you for going to the trouble of setting this all up.
Thank you so much for your time. And before we end this session, may I do one thing, that is singing our national anthem.
Oh, sure. I don't know it though. And I sing really bad.
Start. 3, 2, 1.
जनगणमन अधिनायक जय हे भारत भाग्य विधाता पंजाब सिंधु गुजरात मराठा द्राविड़ उत्कल गंगा विंध्य हिमाचल यमुना गंगा उच्चल जलधि तरंगा तव शुभ नामे जाहे तव शुभ आशीष मागे गाहे तव जय गाथा जन गण मंगलदायक जय हे भारत भाग्य विधाता जय हे जय हे जय हे जय 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 हे.
Jim, he is my colleague and he is the PS teacher, physical science teacher in my school.
Good morning, sir.
Yes.
All right, I'm back. Thank you.
Thank you. Thank you, sir. Good morning, sir. Thank you.
Good morning.
Okay, Jim.
Kishore, sir. My name.
Yeah. Thank you so much, Jim, for your time, and we will see you soon and with one more session. And whenever you visit India, we are ready to give the hospitality and here, and we welcome you to our school. And it's a pride for us to give the hospitality to you when you land here.
Such a kind offer. Thank you so much. There is a possibility I might come to India sometime this year. But I understand it's a very big place. Yes.
Yes, it's big place, but it's not possible. Yes, we can make it to wherever you are.
Okay. All right. It was a pleasure meeting you all. Your English is so good, those of you that are working on it. And I think you must be in a wonderful school because you're asking awesome questions. So thank you very much.
Thank you so
You
much
all
for your time.
have a wonderful day.
So what time is it now over there?
It's 12:15 and I really need to go to bed.
Yes. Thank you so much for your burning the midnight oil today.
Good night.